Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to quite a few new members of our Patreon family. Bill, Hester, Lori, Barbara, Julia, Steve, Alexandra, Rachel, Debbie, and Mitch. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener-supported and ad-free for everyone, and it's very much appreciated. And because you became members in February, you and everyone else who supports us through Patreon or buymeacoffee.com this month will be entered into a raffle, the prize for which is an exclusive episode of Boring Books for Bedtime made just for you. If that sounds like something you'd like to get in on, or you just want to support us so we can keep making new episodes week after week, you'll find links to both Patreon and buymeacoffee.com, where you can support us with a one-time tip, no subscription required, in the show description. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's relax and sleep with some science, with more from The Principles of Chemistry by Dmitri Mendeleev, translated from the Russian by George Kamensky, ARSM of the Imperial Mint, St. Petersburg, and edited by T.A. Lawson, BSc, Ph.D., Examiner in Coal Tar Products, to the City and Guilds of London, Institute Fellow of the Institute of Chemistry. 6th edition, published in 2 volumes by Longmans Green & Co., London, New York, and Bombay in 1897. Let's pick up right where we left off, working our way through the introduction. Let's begin. As the chemical changes to which substances are liable proceed from internal forces proper to these substances, as chemical phenomena certainly consist of motions of material parts, from the laws of the indestructibility of matter and of elements, and as the investigation of mechanical and physical phenomena proves the law of the indestructibility of forces, or the conservation of energy, that is, the possibility of the transformation of one kind of motion into another, of visible or mechanical into invisible or physical, we are inevitably obliged to acknowledge the presence in substances, and especially in the elements of which all others are composed, of a store of chemical energy, or invisible motion inducing them to enter into combinations. If heat be evolved in a reaction, it means that a portion of chemical energy is transformed into heat. If heat be absorbed in a reaction, that it is partly transformed or rendered latent into chemical energy. The store of force or energy going to the formation of new compounds may, after several combinations, accomplished with an absorption of heat, at last diminish to such a degree that indifferent compounds will be obtained, although these sometimes, by combining with energetic elements or compounds, give more complex compounds, which may be capable of entering into chemical combination. Among elements, gold, platinum, and nitrogen have but little energy, whilst potassium, oxygen, and chlorine have a very marked degree of energy. When dissimilar substances enter into combination, they often form substances of diminished energy. Thus, sulfur and potassium, when heated, easily burn in air. But when combined together, their compound is neither inflammable nor burns in air like its component parts. Part of the energy of the potassium and of the sulfur was evolved in their combination in the form of heat. Just as in the passage of substances from one physical state into another, a portion of their store of heat is absorbed or evolved, so in combinations or decompositions, and in every chemical process, there occurs a change in the store of chemical energy, and at the same time, an evolution or absorption of heat. For the comprehension of chemical phenomena as mechanical processes, i.e., the study of the modus operandi of chemical phenomena, it is most important to consider 1. The facts gathered from stoichiometry, or that part of chemistry which treats of the quantitative relation by weight or volume of the reacting substances. 2. The distinction between the different forms and classes of chemical reactions. 3. The study of the changes in properties produced by alteration in composition. 4. The study of the phenomena which accompany chemical transformation. And 5. A generalization of the conditions under which reactions occur. As regards stoichiometry, this branch of chemistry has been worked out most thoroughly and comprises laws of Dalton, Avogadro, Gerhardt, and others, which bear so deeply on all parts of chemistry that at the present time the chief problem of chemical research consists in the application of general stoichiometrical laws to concrete examples, i.e., the quantitative, volumetric, or gravimetric composition of substances. All other branches of chemistry are clearly subordinate to this most important portion of chemical knowledge. Even the very signification of reactions of combination, decomposition, and rearrangement acquired, as we shall see, a particular and new character under the influence of the progress of exact ideas concerning the quantitative relations of substances entering into chemical changes. Furthermore, in this sense, there arose a new, and till then unknown, division of compound substances into definite and indefinite compounds. Even at the beginning of this century, Berthollet had not made this distinction, but Prout showed that a number of compounds contain the substances of which they are composed, and into which they break up in exact definite proportions by weight, which are unalterable under any conditions. Thus, for example, red mercury oxide always contains 16 parts by weight of oxygen for every 200 parts by weight of mercury, which is expressed by the formula HgO. But in an alloy of copper and silver, one or the other metal may be added at will, and in an aqueous solution of sugar, the relative proportion of the sugar and water may be altered, and nevertheless, a homogeneous whole with the sum of the independent properties will be obtained. That is, in these cases, there was indefinite chemical combination. Although in nature and chemical practice, the formation of indefinite compounds, such as alloys and solutions, plays as essential a part as the formation of definite chemical compounds, yet, as the stoichiometrical laws at present apply chiefly to the latter, all facts concerning indefinite compounds suffer from inexactitude, and it is only during recent years that the attention of chemists has been directed to this province of chemistry. In chemical mechanics, it is, from a qualitative point of view, very important to clearly distinguish at the very beginning between reversible and non-reversible reactions. Substances capable of reacting on each other at a certain temperature produce substances which at the same temperature either can or cannot give back their original substances. For example, salt dissolves in water at the ordinary temperature, and the solution so obtained is capable of breaking up at the same temperature, leaving salt and separating the water by evaporation. Carbon bisulfide is formed from sulfur and carbon at about the same temperature at which it can be resolved into sulfur and carbon. Iron at a certain temperature separates hydrogen from water, forming iron oxide, which, in contact with hydrogen at the same temperature, is able to produce iron and water. It is evident that if two substances A and B give two others C and D, and the reaction be reversible, then C and D will form A and B, and consequently, by taking a definite mass of A and B, or a corresponding mass of C and D, we shall obtain in each case all four substances. That is to say, there will be a state of chemical equilibrium between the reacting substances. By increasing the mass of one of the substances, we obtain a new condition of equilibrium, so that reversible reactions present a means of studying the influence of mass on the modus operandi of chemical changes. Many of those reactions which occur with very complicated compounds or mixtures may serve as examples of non-reversible reactions. Thus, many of the compound substances of animal and vegetable organisms are broken up by heat, but cannot be reformed from their products of decomposition at any temperature. Gunpowder, as a mixture of sulfur, niter, and carbon, on being exploded, forms gases, from which the original substances cannot be reformed at any temperature. In order to obtain them, recourse must be had to an indirect method of combination at the moment of separation. If A does not under any circumstances combine directly with B, it does not follow that it cannot give a compound AB. For A can often combine with C and B with D, and if C has a greater affinity for D, then the reaction of AC or BD produces not only CD, but also AB. As on the formation of CD, the substances A and B, previously in AC and BD, are left in a peculiar state of separation, it is supposed that their mutual combination occurs because they meet together in this nascent state at the moment of separation, in statu nascendi. Thus, chlorine does not directly combine with charcoal, graphite, or diamond. There are, nevertheless, compounds of chlorine with carbon, and many of them are distinguished by their stability. They are obtained in the action of chlorine on hydrocarbons, as the separation products from the direct action of chlorine on hydrogen. Chlorine takes up the hydrogen, and the carbon liberated at the moment of its separation enters into combination with another portion of the chlorine, so that, in the end, the chlorine is combined with both the hydrogen and the carbon. As regards those phenomena which accompany chemical reaction, the most important circumstance in reference to chemical mechanics is that not only do chemical processes produce a mechanical displacement, a motion of particles, heat, light, electrical potential, and current, but that all these agents are themselves capable of changing and governing chemical transformations. This reciprocity or reversibility naturally depends on the fact that all the phenomena of nature are only different kinds and forms of visible and invisible or molecular motions. First sound and then light was shown to consist of vibratory motions, as the laws of physics have proved and developed beyond a doubt. The connection between heat and mechanical motion and work has ceased to be a supposition, but has become an accepted fact. And the mechanical equivalent of heat, 425 kilogram meters of mechanical work corresponding with 1 kilogram unit of heat or calorie, gives a mechanical measure for thermal phenomena. Although the mechanical theory of electrical phenomena cannot be considered so fully developed as the theory of heat, both statical and dynamical electricity are produced by mechanical means in common electrical machines or in Graham or other dynamos. And conversely, a current in electric motors can produce mechanical motion. Thus, by connecting a current with the poles of a Graham dynamo, it may be made to revolve, and conversely, by rotating it, an electrical current is produced, which demonstrates the reversibility of electricity into mechanical motion. Accordingly, chemical mechanics must look for the fundamental lines of its advancement in the correlation of chemical with physical and mechanical phenomena. But this subject, owing to its complexity and comparative novelty, has not yet been expressed by a harmonious theory or even by a satisfactory hypothesis, and therefore we shall avoid lingering over it. A chemical change in a certain direction is accomplished not only by reason of the difference of masses, the composition of the substances concerned, the distribution of their parts, and their affinity or chemical energy, but also by reason of the conditions under which the substances occur. In order that a certain chemical reaction may take place between substances which are capable of reacting on each other, it is often necessary to have recourse to conditions which are sometimes very different from those in which the substances usually occur in nature. For example, not only is the presence of air, oxygen, necessary for the combustion of charcoal, but the latter must also be heated to redness. The red-hot portion of the charcoal burns, that is, combines with the oxygen of the atmosphere, and in so doing evolves heat, which raises the temperature of the adjacent parts of charcoal so that they burn. Just as the combustion of charcoal is dependent on its being heated to redness, so also every chemical reaction only takes place under certain physical, mechanical, or other conditions. The following are the chief conditions which exert an influence on the progress of chemical reactions. A. Temperature. Chemical reactions of combination only take place within certain definite limits of temperature and cannot be accomplished outside these limits. We may cite as examples not only that the combustion of charcoal begins at a red heat, but also that chlorine and salt only combine with water at a temperature below 0 degrees. These compounds cannot be formed at a higher temperature, for they are then wholly or partially broken up into their component parts. A certain rise in temperature is necessary to start combustion. In certain cases, the effect of this rise may be explained as causing one of the reacting bodies to change from a solid into a liquid or gaseous form. The transference into a fluid form facilitates the progress of the reaction because it aids the intimate contact of the particles reacting on each other. Another reason, and to this must be ascribed the chief influence of heat in exciting chemical action, is that the physical cohesion, or the internal chemical union of homogeneous particles, is thereby weakened, and in this way the separation of the particles of the original substances and their transference into new compounds is rendered easier. When a reaction absorbs heat, as in decomposition, the reason why heat is necessary is self-evident. At the present day, it may be asserted upon the basis of existing data respecting the action of high temperature that all compound bodies are decomposed at a more or less high temperature. We have already seen examples of this in describing the decomposition of mercury oxide into mercury and oxygen, and the decomposition of wood under the influence of heat. Many substances are decomposed at a very moderate temperature. For instance, the fulminating salt which is employed in cartridges is decomposed at a little above 120 degrees. The majority of those compounds which make up the mass of animal and vegetable tissues are decomposed at 200 degrees. On the other hand, there is reason to think that at a very low temperature, no reaction whatever can take place. Thus, plants cease to carry on their chemical processes during the winter. Raoul Pictet, in 1892, employing the very low temperatures, as low as minus 200 degrees Celsius, obtained by the evaporation of liquefied gases, has recently again proved that at temperatures below minus 120 degrees, even such reactions as those between sulfuric acid and caustic soda or metallic sodium do not take place. If a given reaction does not take place at a certain low temperature, it will at first only proceed slowly with a rise of temperature, even if aided by an electric discharge, and will only proceed rapidly with the evolution of heat when a certain definite temperature has been reached. Every chemical reaction requires certain limits of temperature for its accomplishment, and doubtless many of the chemical changes observed by us cannot take place in the sun, where the temperature is very high, or on the moon, where it is very low. The influence of heat on reversible reactions is particularly instructive. If, for instance, a compound which is capable of being reproduced from its products of decomposition be heated up to the temperature at which decomposition begins, the decomposition of a mass of the substance contained in a definite volume is not immediately completed. Only a certain fraction of the substance is decomposed, the other portion remaining unchanged, and if the temperature be raised, the quantity of the substance decomposed increases. Furthermore, for a given volume, the ratio between the part decomposed and the part unaltered corresponds with each definite rise in temperature until it reaches that at which the compound is entirely decomposed. This partial decomposition under the influence of heat is called dissociation. It is possible to distinguish between the temperatures at which dissociation begins and ends. Should dissociation proceed at a certain temperature, yet should the product or products of decomposition not remain in contact with the still undecomposed portion of the compound, then decomposition will go on to the end. Thus, limestone is decomposed in a lime kiln into lime and carbonic anhydride because the latter is carried off by the draft of the furnace. But if a certain mass of limestone be enclosed in a definite volume, for instance in a gun barrel, which is then sealed up and heated to redness, then, as the carbonic anhydride cannot escape, a certain proportion only of the limestone will be decomposed for every increment of heat, the rise in temperature higher than that at which dissociation begins. Decomposition will cease when the carbonic anhydride evolved presents a maximum dissociation pressure corresponding with each rise in temperature. If the pressure be increased by increasing the quantity of gas, then combination begins afresh. If the pressure be diminished, decomposition will recommence. Decomposition in this case is exactly similar to evaporation. If the steam given off by evaporation cannot escape, its pressure will reach a maximum corresponding with the given temperature, and then evaporation will cease. Should steam be added, it will be condensed in the liquid. If its quantity be diminished, that is, if the pressure be lessened, the temperature being constant, then evaporation will go on. We shall afterwards discuss more fully these phenomena of dissociation, which were first discovered by Henri St. Clair de Ville. We will only remark that the products of decomposition recombine with greater facility the nearer their temperature is to that at which dissociation begins, or, in other words, that the initial temperature of dissociation is near to the initial temperature of combination. B. The influence of an electric current and of electricity in general on the progress of chemical transformations is very similar to the influence of heat. The majority of compounds which conduct electricity are decomposed by the action of a galvanic current, and as there is great similarity in the conditions under which decomposition and combination proceed, combination often proceeds under the influence of electricity. Electricity, like heat, must be regarded as a peculiar form of molecular motion, and all that refers to the influence of heat also refers to the phenomena produced by the action of an electrical current, with this difference, only that a substance can be separated into its component parts with much greater ease by electricity, since the process goes on at the ordinary temperature. The most stable compounds may be decomposed by this means, and a most important fact is then observed, namely that the component parts appear at the different poles of electrodes by which the current passes through the substance. Those substances which appear at the positive pole or anode are called electronegative, and those which appear at the negative pole or cathode, that in connection with the zinc of an ordinary galvanic battery, are called electropositive. The majority of non-metallic elements, such as chlorine, oxygen, etc., and also acids and substances analogous to them, belong to the first group, whilst the metals, hydrogen, and analogous products of decomposition appear at the negative pole. Chemistry is indebted to the decomposition of compounds by the electric current for many most important discoveries. Many elements have been discovered by this method, the most important being potassium and sodium. Lavoisier and the chemists of his time were not able to decompose the oxygen compounds of these metals, but Davy showed that they might be decomposed by an electric current, the metals sodium and potassium appearing at the negative pole. Now that the dynamo gives the possibility of producing an electric current by the combustion of fuel, this method of Sir Davy is advantageously employed for obtaining metals, etc., on a large scale. For instance, sodium from fused caustic soda, or chlorine from solutions of salt. C. Certain unstable compounds are also decomposed by the action of light. Photography is based on this property in certain substances, for instance in the salts of silver. The mechanical energy of those vibrations which determine the phenomena of light is very small, and therefore only certain, and these generally unstable compounds can be decomposed by light, at least under ordinary circumstances. But there is one class of chemical phenomena dependent on the action of light, which forms as yet an unsolved problem in chemistry. These are the processes accomplished in plants under the influence of light. Here there take place most unexpected decompositions and combinations, which are often unattainable by artificial means. For instance, carbonic anhydride, which is so stable under the influence of heat and electricity, is decomposed and evolves oxygen in plants under the influence of light. In other cases, light decomposes unstable compounds, such as are usually easily decomposed by heat and other agents. Chlorine combines with hydrogen under the influence of light, which shows that combination, as well as decomposition, can be determined by its action, as was likewise the case with heat and electricity. D. Mechanical causes exert, like the foregoing agents, an action both on the process of chemical combination and of decomposition. Many substances are decomposed by friction or by a blow, as for example the compound called iodide of nitrogen, which is composed of iodine, nitrogen and hydrogen, and silver fulminate. Mechanical friction causes sulfur to burn at the expense of the oxygen contained in potassium chlorate. Pressure affects both the physical and chemical state of the reacting substances, and together with the temperature determines the state of a substance. This is particularly evident when the substance occurs in an elastic gaseous form, since the volume, and hence also the number of points of encounter between the reacting substances, is greatly altered by a change of pressure. Thus, under equal conditions of temperature, hydrogen, when compressed, acts more powerfully upon iodine and on the solutions of many salts. E. Besides the various conditions which have been enumerated above, the progress of chemical reactions is accelerated or retarded by the condition of contact in which the reacting bodies occur. Other conditions remaining constant, the rate of progress of a chemical reaction is accelerated by increasing the number of points of contact. It will be enough to point out the fact that sulfuric acid does not absorb ethylene under ordinary conditions of contact, but only after continued shaking, by which means the number of points of contact is greatly increased. To ensure complete action between solids, it is necessary to reduce them to a very fine powder and to mix them as thoroughly as possible. Monsieur Spring, the Belgian chemist, has shown that finely powdered solids which do not react on each other at the ordinary temperature may do so under an increased pressure. Thus, under a pressure of 6,000 atmospheres, sulfur combines with many metals at the ordinary temperature, and mixtures of the powders of many metals form alloys. It is evident that an increase in the number of points or surfaces must be regarded as the chief cause producing reaction, which is doubtless accomplished in solids as in liquids and gases in virtue of an internal motion of the particles, which motion, although in different degrees and forms, must exist in all the states of matter. It is very important to direct attention to the fact that the internal motion or condition of the parts of the particles of matter must be different on the surface of a substance from what it is inside, because in the interior of a substance, similar particles are acting on all sides of every particle, whilst at the surface they act on one side only. Therefore, the condition of a substance at its surfaces of contact with other substances must be more or less modified by them. It may be in a manner similar to that caused by an elevation of temperature. These considerations throw some light on the action in the large class of contact reactions, that is, such as appear to proceed from the mere presence or contact of certain special substances. Porous or powdery substances are very prone to act in this way, especially spongy platinum and charcoal. For example, sulfurous anhydride does not combine directly with oxygen, but this reaction takes place in the presence of spongy platinum. The above general and introductory chemical conceptions cannot be thoroughly grasped in their true sense without a knowledge of the particular facts of chemistry to which we shall now turn our attention. It was, however, absolutely necessary to become acquainted on the very threshold with such fundamental principles as the laws of the indestructibility of matter and of the conservation of energy, since it is only by their acceptance and under their direction and influence that the examination of particular facts can give practical and fruitful results. And with that, we have at last reached the end of the introduction of the principles of chemistry. I say the end, but I'm not including the 40 pages of footnotes that follow it. If you'd like to read those for yourself, and quite frankly, they're kind of interesting, as always, I'll leave a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, the best place to catch me is on Twitter at BoringBooksPod, or drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.